wonderful thing about Untitled, he just published a volume of his collected papers, which were entitled 7 Decades of Physics. So I've always seen for myself and everybody in this room, if you managed to do physics for 7 decades, that would be a real achievement. And Hans Bethe managed it, so did Charlie Towns, actually. Ted Duvall at Stanford is pretty close, and I just did the arithmetic before coming here and realized, David, I think you're only 3 years off, right? So Bardeen-Pines did brilliant research. All of us know anybody in quantum physics, but also in astrophysics and nuclear physics knows about the impact of his work going back to, I think his first paper was in 1950, and he had an enormous impact on highly correlated electronic systems, and I think superconductivity is one of our gurus during the last couple of decades, and he's done many other things. So I'll just read what he's currently doing in terms of his position. So he's the founder and resident of the San Jose Institute, founding director emeritus of the Institute for Complex Adaptive Matter, which is a UC-wide program, distinguished research professor of physics at UC Davis, research professor of physics, professor emeritus of physics, and of electrical engineering and computer science in the Center for Advanced Studies, University of Illinois at Champaign, where he spent most of his career. David's actually here as part of a set of lectures given by winners of the Julia Edgar Lilienfeld Prize of the American Physical Society. His predecessors who have held this prize in the past include Marvin Cohen, Stephen Hawking, Kip Thorne, Lisa Randall, Frank Wilczek, and his successor after him is Martin Rees. So this is a pretty extraordinarily distinguished group. And the prize specifically is given to people who are able to explain our profession and what we do to a diverse audience. Before Dave comes up to talk to us, I'll read actually the citation from the Lilienfeld Prize. For his seminal contributions to our understanding of emergent behavior in quantum matter, that's what he's going to tell us about today, including plasmons and quasi-particles, and the consequence of electron interactions in solids, mechanisms of superconductivity, both conventional and Q-based superconductors, nuclear and celestial superfluidity, most recently, heavy electron emergence of superconductivity in condo lattice materials, and for his effectiveness in communicating these discoveries and a new emergent paradigm for the broader scientific community. Actually, I sent David back to Berkeley. I was asking him on the way here whether or not he took classes here, and I could not have been a professor because I was only 2 years old. David,
Thank you very much, Bob. It's a total pleasure for me to be back in Berkeley. It played an enormous part in my early life in physics, and I thought I'd tell you a little bit about that before I get into my talk proper. I arrived in Berkeley in August of 1941. I'm 17 years old, I'm an undergraduate. I didn't have the slightest idea of what I wanted to do. I knew I was pretty good at math. I'd been to an experimental college a year before called Black Mountain College. Have any of you ever heard of Black Mountain? No, okay. It was quite an interesting place. It had 90 students all in all, and what it had as one of their professors, and they didn't have many, was Nathan Rosen, who was at that time fresh from working with Einstein and unable to get a job anywhere in the United States in 1940, except at Black Mountain, where he got room and board for himself and his family and $100 a month. And I was his prize student. I was the only of those 90 kids, I was the only one who had any mathematical interest or abilities. So I took a seminar with him. I learned calculus from Nathan. Toward the end of the year, he said, David, you know, I think you might be a theoretical physicist. I looked at him. I said, Nathan, that's very unlikely. Physics was my worst topic in high school. I managed to get a B+. It's the only B I had in high school because it was taught by the baseball coach. And I realized later they figured that's the only place, that's where he would do the least damage, and that's true. So I had no sense of becoming a physicist. Came to Berkeley after this year in Black Mountain. And then as a junior here, I took a course, an undergraduate course in quantum theory taught by one of Oppenheimer's former students, Joe Weinberg. He was a great teacher. It was a wonderful course, and that decided me. I wanted to be a theoretical physicist. I hung out a lot with Joe's house and heard story after story about Robert Oppenheimer. So I became very specific. I wanted to be a graduate student at Berkeley and work with Oppenheimer. Went off to the Navy for a couple of years. Came back here. Oops. Came back here in. Is that better? Is that better? Higher up?
Higher up, all the time. Yeah.
Okay, is this better? Let's hope. We'll get it. So, came back in August of '46 and had my first glimpse of Oppenheimer on the stairs of this building, LeConte. Standing outside, I'd just come back from lunch. Oppenheimer walks by, and it's sort of trailed by a group of people who recognized him. And he was pretty annoyed about this. He whipped around when he got to the top of the stairs and said to the followers, "You look funny too." So I spent that. The other thing that happened to me within about a week is I met my wife to be at a graduate student mixer and married her a year and a half later. We were married for some 67 years, so a really important beginning for me in Berkeley. To take Oppenheimer's course on quantum theory was a joy and a delight because he was an extraordinarily charismatic teacher and a wonderful, just to watch him move around, always with a cigarette in his hand and wondering at what moment will he try to write on the board with his cigarette rather than the piece of chalk in the other. Never did. And that was a great time to be a graduate student here because we were a little bit older than your average graduate student. And a lot of the faculty were accustomed to being in a small department where you interacted as much with the graduate students as you did with your fellow faculty members. So I was lucky enough to hang out at the Oppenheimers, and the other couple with whom I hung out a great deal were Bob and Charlotte Serber. And I met all of the greats of the time, from Ernest Lawrence to the young, I think he was not even in the department, he was up at the radiation lab, Pete Panofsky. Herb York was a fellow graduate student at the time. So it was a time when, I should really tell you about a New Year's Eve party that I went to at the Serbers, at which people, in those days, you really drank quite a lot, and you drank early and you drank often. So Ed McMillan is there, quite drunk, and he asked Frank Oppenheimer if he could borrow his hat, which he did. And he proceeded to then he found a stapler somewhere, and he created for Frank a perfect circle of staples in this marvelous black Stetson hat. Okay, so it was a different time, and people behaved in a really different way, and was absolutely centered around Oppenheimer for sure. But a lot of gifted experimental people, and an exciting time in the department. I stayed only 1 year because Oppenheimer left, and he offered to take a few of us with him. I followed him to Princeton. He became way too busy to have any more graduate students, but always regarded me as one of his students. And I felt that he was certainly a major mentor in my life. And he became so in another way, because the summer I got married was 1948, and I had arranged with Oppenheimer that I could come here and be the reader, because the last time he taught his course in quantum theory was that summer of 48. So I was the reader for his course. And he and Bob Serber had organized a seminar on quantum electrodynamics, which of course a graduate, so which of course I took. And it's there that I realized I might even succeed in being a theoretical physicist, because my assignment was to tell the seminar about the segment of the Pocono notes which John Wheeler had taken on Schwinger's lectures, and I was to explain gauge invariance. I knew nothing about field theory, so I read Wenzel's book in German as best I could, went through the notes as carefully as I could, and about halfway through my talk, I realized suddenly, looking at my audience, I knew more about what Schwinger had done than anyone in the audience, including Oppenheimer and Serber. And that gave me a lot of confidence in terms of being able to learn as a young man, read something, and actually be able to talk about it in a way that people could listen to and learn from it. And so I went on from there. And the rest of my talk will describe a lot of what I did afterwards. So what I'm trying to do in this talk is to practice what I preached in an article with Bob Laughlin, which we had called cheerfully The Theory of Everything. We were really annoyed with the notion that was being put forth by the string theorists at that time that they understood it all. And we pointed out to them that whatever they understood had nothing to do with the real world. It had nothing to do with experiment, and that, in fact, there is no theory of everything. You could write down the Hamiltonian for everything that relates to the human condition. It's pretty easy. It's a collection of electrons and ions interacting with each other. You can put in whatever kind of environment you want to. But because what you're dealing with is the unexpected consequences of the interactions of electrons and ions in their environment, you're dealing with emergent behavior. And what you try to do then as a theoretical physicist, you don't try to write down ultimate equations. You catalog and understand and organize emergent behavior in its many different guises. And after Bob and I wrote that paper, I realized that describes my life up until that time and my life afterwards. So in 1950, I finished my PhD work with David Bohm. And what I was able to do and what we did in the papers that followed was show that the main consequences of the long range of the Coulomb interaction, which led to any number of divergences if you tried to deal with it, was to give rise to a collective mode, quantized plasma oscillations. These have a very high frequency noted on the transparency. And about the time that I'm grinding away on my thesis, which was based on a formalism that Schwinger had introduced in a series of canonical transformations to start off with plasmon quantized plasma oscillations interacting with electrons, transform away that interaction, you wound up with the collective modes slightly modified by the interaction with the electrons, and a set of electrons interacting with the short-range interaction, which you could then deal with. Conyers-Herring told us that our quantized oscillations had in fact been seen in inelastic electron scattering experiments, and the evidence looked pretty good, and it only got better. And when I gave a Solvay lecture on the topic in 1954, Neville Mott, who'd read our paper, said, you know, you should really see this on about just anything, because interband transitions at these high energies are pretty unlikely. And a simple sum rule argument shows that the valence electrons should almost always carry out oscillations at very nearly the free electron frequency. And by 55, it really became clear that plasmons were here to stay. And it was a special session of the March meeting that had been organized by one of the leading experimentalists who was studying the phenomena of inelastic electron scattering, Ladislav Martin. He invited me to talk, invited John Slater. We had different interpretations of the experiment. Mine was in terms of the quantized plasma oscillations. I thought I made a really good case for it. John Slater, total believer in band theory, ignoring electron interaction, explained them all with interband excitations. Martin did something nobody would dream of doing today. At the end of our two talks and the discussion, he then called upon the audience to vote. Who was right, Slater or me? Slater won by 2-1. So much for popular opinion. I mean, no question, seniority won out over ideas in that audience. I once told this story to my friend Murray Gell-Mann, who used it to, as one of his arguments, to say it's not solid state physics, it's squalid state physics. So what is interesting is these plasmons, which did join electrons and magnons as elementary excitations and phonons, of course, is that they turned out to be of practical use. And that's because, first of all, they were shown to exist at the surface. You have waves of charge bound at the surface. These are surface plasmons. Well, Rufus Ritchie figured that out. And then the applied physicists realized, hey, this is really a great control mechanism because we can vary the material we deal with, vary the surface. We can control it in a lot of interesting ways. And a field called plasmonics emerged out of sort of nowhere. By 2005, Harry Atwater, one of the pioneers, named it plasmonics, wrote about it for Scientific American. And one of his students, who's now at Stanford, Brugner, in a talk he gave in 2015, 10 years later, said, the field is doubling about every 3 years, and there are about 10,000 papers a year devoted to it. So curiosity-driven science is absolutely the way to go. And every now and then it may turn out to have applications, is the takeaway message. Right. If at first you don't succeed. Okay, is that better?
Is it better? No? Let's see, where's your...
Maybe the machine is not on.
No, this is on. There.
Okay, I now have a maximum volume.
Okay, it's working now.
All right. Try again. Say something.
Is it working now? Okay, thank you. Okay, so plasmons are not the only example of collisionless collective modes. All of the modes you see in the helium liquids have the same basic origin, but can't be dealt with by the Baire interaction. The Baire interaction gets modified, which is a very strong short-range repulsion, the long-range attraction is modified in the liquid. And we figured out a way to describe that modification and introduce the kinds of restoring forces that by then it was clear you needed for the helium liquids. You needed both the scalar field and the backflow field introduced by Richard Feynman. And with that, you get a simple expression for the density response function, which is what you measure in a neutron scattering experiment. And we came up with a really simple phenomenological way of sorting out what was the influence of those short-range correlations. Namely, that they tend to keep the helium atoms away from each other. They don't sample the full, strong, very strong repulsive short-range interaction. But on the other hand, the long-range part remains the same. So you can describe the short-range part with a simple pseudo-potential and then make a lot of physical arguments, combine it with some rule arguments and experiments on compressibility and spin susceptibility. And you can sort out what must be those potentials for both helium-4 and helium-3 and do really a terrific job of understanding the experiments. It's, I think, a great triumph of combining one's understanding of basic physics with a little bit of phenomenology. It can go a very long way. Next example, superconductivity. This was sort of the problem in physics from its discovery in 1911 till it was understood in 1957. Following its discovery, everyone had a go at it. Einstein, Bohr, Heisenberg, Lee, Yang, Feynman, Bardeen several times, all of them, Ginzburg, Landau, et al. All of the greats in theoretical physics tried to explain superconductivity and failed. Why? They couldn't understand either predict the mechanism or the emergent order that characterized it, the ability of metals to carry current without any resistance and shield out magnetic fields. Why did it take so long? Well, for 20 years, we didn't have a good quantum theory of matter, but we did after 20 years. It still took another 20 plus years before we had a smoking gun. And it came from experiment. And the experiments on the isotope effect that showed that the transition temperature depended on the mass of the ions in the metal that you were studying. And it goes as roughly 1 over the square root of mass, and that says, okay, the phonons, the elementary excitations of the lattice, must be involved somehow. But the question is how do phonons influence the properties of the electrons? Well, the first pass was made independently by Herbert Frohlich and John Bardeen, whose passion was to understand superconductivity. And they failed. They thought it was the self-energy. The electron moves along, emits a virtual phonon, reabsorbs it, that changes its mass, and they tried to argue, well, this is what gives us superconductivity. Doesn't work. Frohlich then said, well, maybe if you go to second-order perturbation theory, you can calculate the phonon-induced interaction. An electron emits a virtual phonon, a certain second electron receives it, so you can think of it as a polarization effect. This gives rise to an attractive frequency-dependent interaction. His suggestion went nowhere for one reason, because the community said, hey, you forgot about the Coulomb interaction. That's big and repulsive. So how on earth can this little frequency-dependent interaction do it? Well, it's like I'll put it, you can't repeal Coulomb's law. With John Bardeen, I'm there as a postdoc in 1954, in describing to him my tentative efforts to extend what Bohm and I had done to electrons, ions in a lattice. And John, I was halfway along, and John pointed out I'd forgotten one thing, the possibility that you could get a modification in the phonon field as well as the electron field. And we put that in and wrote a paper about it and found that the screened phonon-induced interaction could win out over the screen repulsive interaction. And we argued, well, this is the way to go. And this is sort of what it looks like. You have two terms. You have a repulsive screened Coulomb interaction, the attractive phonon-induced interaction. If you ignore the effects of periodicity, the two cancel each other at omega equals 0. You go to finite frequencies, and the phonon-induced interaction wins out. The next big step was taken by Leon Cooper when he developed a toy model to describe what Bardeen and I had derived. He said, let me look at the consequences of an attractive interaction, which is constant, but attractive for frequencies within a Debye energy of the Fermi surface, and is 0 otherwise, so quite tractable. And what he found was, looking at a pair of electrons outside the Fermi sea, if he neglected any other effects and just looked at their multiple scattering, he found the valence state, and he thought that was really interesting. It was subsequently shown to allow for a more complete theory with the scattering of holes as well as electrons. It gives rise to an instability. But this is the key to superconductivity. An attractive interaction causes the Fermi surface to become unstable. Okay, that's step one. But step two was the key step. And that was made by Bob Schrieffer, who wrote down a wave function for the ground state of a superconductor in slow-lying excited states, in which the emergent superfluid order was the macroscopic occupation of a single quantum state, which is made up of pairs of electrons of opposite spins. If these condense into a single quantum state, it's not Bose-Einstein condensation because the pairs are big. They typically involve thousands of, the distance between them is order 10 to the minus 4 centimeters, not 10 to the minus 8 centimeters. So it's not Bose-Einstein condensation, but something quite different. And this was the key to making the theory. Bob went home from New York where he had the idea and showed it to Cooper and Bardeen, who said, okay, this is it. The three of them in a couple of weeks produced the first version of BCS. And this was the theory that explained everything about superconductivity. And one thing it didn't explain and that I had a hand in was the rules, the empirical rules that Bernd Matthias had developed for what would be a superconducting metal and what would not. And I'm lecturing about BCS to my class in Princeton because with Elihu Abrahams and my student Philippe Noziere, we had figured out from the letter that BCS sent to PRL, we'd figure out what was actually going out sufficiently that I could talk about it to a graduate student class. And I realized, let me have a go at the Matthias rules. I made a simple model and found, yeah, the requirement that the net interaction be attractive would do it. But what you needed to do that were the Umgop processes possible because you've got a lattice, which gallium will never superconduct. So then next step, I go off to Copenhagen and lecture about BCS at the Bohr Institute. And I should tell you a story there. Before I lectured, both Ove Bohr and Ben Morrison took me aside and warned me that I could well encounter a major problem, because 2 weeks earlier, John Blatt had described his theory of superconductivity based on boson condensation of preformed pairs. And Papa Bohr had stopped him after about a minute and a half. And he didn't like what Blatt was doing. And Blatt is trying to go on, and Bohr is absolutely implacable in interfering with his presentation. So Owen and Ben are saying to me, be warned, David, Niels Bohr may not be happy about what you're doing. So I took my precautions. I decided I have to give the bottom line in the first 2 minutes, and then we'll see what happens. And I was sufficiently convincing, got through the lecture in fine fashion, and in the process pointed out that after all this, the Institute for Nuclear Theory, why shouldn't one get pairing outside the closed shells of nuclei? Hadrons interact, they're attractive. Why not have pairing phenomena? And Owen Ben loved the idea, and we worked it out during the summer. It turns out to explain a number of pairing correlations in nuclei. And of course, my reward for my lecture was then to have to spend an hour with Niels Bohr talking about superconductivity. That was it was exciting as it could be, and it was sheer hell. Because you sat at that time with Bohr, and he would start to talk a little bit, and virtually unintelligible, any language, Danish, English, you name it, very hard to understand, because he is talking and at the same time he's lighting his pipe. And there's interference in the two. And so talking to him was a total adventure. You were never quite sure what he was saying, and you were never quite sure what the impact of what you were saying was having on, but it was sure exciting. So the next step was taken by Arkady Migdal, who knew about neutron stars and who had read our paper, and he said, well, if indeed that you have every indication of nuclear superfluidity and finite nuclei, if you have a star made up entirely of neutrons, that is going to be a superfluid star. And then his colleagues, Vitaly Ginzburg and Kirchner, said, yeah, but think about the fact stars rotate. Therefore, if you've got a neutron star that's rotating, it's going to be filled with vortices, just as superfluid helium is. And things stood that way until Jocelyn Bell discovered pulsars. What she had to do was convince her thesis supervisor, Tony Hewish, that these very regular oscillations she saw were real and not the product of some artificial interfering agent sitting down the road. They initially called them LGMs, for little green men. There's no idea what was bringing it about, but within the year it became clear. Pulsars are rotating neutron stars. They have very high magnetic fields. If you conserve flux in the collapse of a dying star of, say, 6 or 8 solar masses, the core collapses. It's got a field of order of Gauss that gets amplified to fields of order 10 to the 12th Gauss. This can pull charged particles off the surface, form a jet. That's what you eventually see as a pulsed radio wave. Next step to showing that in fact they are celestial superfluids came with the fact that one of the young pulsars, the Vela pulsar, was observed to glitch. Instead of slowing down in very regular fashion, which is because it's giving off energy, which you see as pulsed radio waves and elsewhere in the spectrum, it suddenly sped up. Now the fact that they're able to see it at all meant that there had to be superfluid there, because the characteristic time for a signal, if the star is made up of normal matter, would be something like 10 to the minus 4 seconds. That would have been the response time to whatever caused the glitch. No, the response time was clearly days to weeks in the case of the Vela pulsar. So the question is, what caused that? The first thing a number of us tried was the idea of a starquake. That does not work, because the time starquake would happen because the star is spinning down, you've got a solid crust, it comes under strain from the spin down, and it will sooner or later quake. But if you do the back of the envelope or better calculations, turns out the time between the kinds of starquakes required to explain the Vela pulsar would be of order of hundreds to thousands of years, and 2 years later the Vela pulsar glitched again. So that was not the origin. Phil Anderson figured it out because he had worked on type 2 superconductors. He knew there that flux lines can be pinned to imperfections. And he said, okay, if you've got pinning of the vortices in the rotating superfluid in the Vela pulsar or other pulsars, if they're pinned, then the glitch could be the catastrophic unpinning of the vortices. And that turned out to be correct. So a group of us in Aspen worked for about 4 years developing a phenomenological theory, which has turned out to be amazingly successful. And you see a quite complicated response after each Vela glitch, and it's a mixture of having strong, weak, and super weak regions of pinning in the crust of the star. And you see each of these responding independently with quite different response time. And you also see a characteristic nonlinear response. I won't go into the detail. The point is that astronomers have been looking continually at the Vela pulsar, so one has a real test, something like 17 or 18 glitches. They're listed there, some 19 glitches in all. The upper right-hand side shows the observational data after a number of glitches, and then you see them superimposed in the lower right. And the line that's drawn through them is the line that is predicted by our theory when you put in the various response times. So there can be little question that we've got now 172 pulsars that have been seen to glitch, and it tells you the amount of cosmic superfluid that's already been observed is some several solar masses. Okay, that's 10 to the 34th grams of superfluid matter. That's quite a lot more than we've ever managed to put forth on Earth or observe. So that's where the action is up there in the sky. And the transition temperature, by the way, is also up there. It's of order 10 to the 6th Kelvin. So really, neutron stars are just great to work on. If you love condensed matter and you're willing to learn some nuclear physics, you can have a marvelous time working on theories of neutron stars. That's a current picture. It's a few years old, but that just shows there's an interior that we don't fully understand. Then all of the action is in the inner crust, where you have superfluid neutrons pinned to the crustal nuclei. That's what gives rise to the glitches. Okay, on to high TC. In 1986, high TC was discovered. The question again, what's the mechanism? What's the pairing state? Clearly a really different class of materials. Jacques Friedel described the way the theoretical community responded to this. He said, oh, each of us had sitting in our closet somewhere, an old moth-eaten sweater representing an interesting theory of superconductivity, which built on the idea of attraction, but attraction came from something other than phonons. So we hauled out our sweaters and tried to persuade the world that this was the sweater we ought to wear. And those who'd worked on the Hubbard model tried to solve the Hubbard model and show this would give rise to ITC. Phil Anderson had worked on RVB. He said, oh, this must be it. And two groups took a different point of view. A group in Urbana and a group in Tokyo, led by Maria and Casarueda. What we looked at was the possibility that we were seeing the magnetic analog of the phonon-induced attraction between quasi-particles. But what is providing the glue then are quantum critical fluctuations induced by the fact that all of these materials are near a quantum critical point. The end of antiferromagnet, they all are antiferromagnets at some doping or pressure. And that end point then gives rise to quantum critical fluctuations that you can describe very nicely. And they're given the spin-spin response function is given at the bottom part of the next slide. And you can show that you can see these quantum critical fluctuations very clearly in the NMR spin lattice relaxation rate. You get a good fit to what goes on with that particular response function. So what we did in Urbana was say, let's then ask, what does the effective interaction look like? It'll be just proportional to that spin-spin response function. And this is what it looks like. That's the magnetic quasi-particle interaction between a pair of spins. And a graduate student, who's a very bright kid. I had no idea that he was computationally literate and in fact computationally imaginative. And he was able to use the high-speed computers then present in Urbana to show that when you allowed for the frequency dependence of that interaction, you could really get a high-temperature superconductor. It increased by a factor of 10 the earlier estimates of how effective the spin fluctuation interaction could be if you just kind of averaged over everything. If you allow for the frequency dependence, TC goes up about a factor of 10. So our conclusion, also reached by the Japanese, was the pairing state would always be dx squared minus y squared, and you could really get high TC. So it was, for those of you who were around in the early 90s, you may very well remember at any meeting on high TC, there would be wind down to a debate between me and Phil Anderson as to what was the mechanism, what was going on. Phil was absolutely convinced that it was RVB, and he really did not believe in the possibility of a spin fluctuation-induced attractive interaction. But I won that battle because the NMR experiment showed that it was clearly D-wave, and then we had direct experiments carried out in Urbana and in at IBM using really pure samples that showed you had D-wave pairing, no question about it. So I asked our mutual friend Elihu Abrahams, well, what's Phil going to do now? He said, won't bother him at all. He'll find a way to get D-wave with RVB. And that's what he did. So most of the experiments since the mid-90s have really focused on the pseudogap. But a little thought and a lot of experimental work shows that the pseudogap state is the state of the local moments that are there coexisting with the itinerant electrons. you have two fluids throughout almost the entire doping range of the cuprates. One fluid are the local spins, which then order in the pseudogap state. They have to get rid of their entropy somehow, so they do so by going into the pseudogap state. The other are the itinerant electrons, and they get rid of their entropy by going superconducting at lower temperatures. And so, and the sort of final proof in all of that was that there's a quantum critical point you can identify in transport measurements. This is work by Bardeen et al. With Louis Taillefer and Canada. And it shows that it's exactly the same point at which you get rid of the pseudogap, you also get rid of localized behavior. So around 0.19, you have a second quantum critical point. It's a mark. It's the metal insulator transition for the itinerant electron, for the local moments. You get rid of all the local moments, you're just left to the right of that with itinerant electrons that can superconduct. And this is the kind of candidate phase diagrams that arise. I'll just show there. You can look at the literature and find them in more detail. But they all suggest that what's going on in the normal state is a mixture of an anomalous Fermi liquid, that's the AFL, and either a quantum critical spin liquid of local moments, or at lower temperatures, they form the pseudogap state. And that has to be the starting point for any subsequent theories. And these are the experiments which, again, the Taillefer group that show that this is not restricted to the cuprates. It's true for heavy electrons. It's true for essentially organics. It's true for all of the unconventional superconductors so far. So you're looking at a common mechanism and a common pairing state. You may get a different pairing state from dx squared minus y squared, depending on the background band structure, but the mechanism is the same. So my final topic for you is to tell you about Kondo lattice materials. For those of you who are not condensed matter physicists, what's fascinating about these materials, you've got, start off with a lattice of local moments, usually F electrons, but can be D electrons. You start off with a lattice of local moments. They are coupled to background conduction electrons. What you expect naively is, okay, this is going to be the single ion Kondo effect writ large, in which the magnetic field of the local moment gets screened out by the conduction electron. This isn't what happens at all. Phenomenologically, we're able to sort out what is the underlying behavior of these Kondo lattice materials. And I remind you that the mass of the electrons can easily exceed the mass of the mu meson. They can be between 2 and 500 times the bare electron mass. And these are the objects that can superconduct at quite high temperatures compared to the Fermi energy, their Fermi energy, which of course is vastly lowered by the heavy mass. Why do they have such a large mass? Because the electron that moves is entangled really with the local spins. It remembers it came from the local spins, and its mass can grow dramatically depending on the coupling between the nearest neighbor local moments. How did we find our way into this problem? It was, again, phenomenological. By 2003, we had a terrific set of new materials called the 115 materials. Cerium, cobalt, indium-5, cerium, rhodium, indium-5, cerium, iridium, indium-5, 115 materials. And you could begin to play with them as a function of doping and pressure. And the great thing about them is they are really clean compared to, if you make a sample, you can easily make a sample which is as good, as clean as the very best cuprates, and it might take you years to figure out how to make. They really make pure samples very easily. And it was pretty clear that in some ways this hybridization process was not instantaneous. The local moments, as they hybridize, they're still around. You have residual interactions between the local moments, and these can bring about antiferromagnetic behavior. But on the other hand, the itinerant heavy electrons were a very peculiar beast. They were not a Landau Fermi liquid with well-behaved behavior, following Landau's gorgeous theory of the Fermi liquid. They were something else. They showed scaling behavior, universal behavior, and only one temperature was involved, T star. And that turned out, we were able to show, this is the Heisenberg interaction, the RKKY interaction between nearest neighbors. So rho times T star is rho J squared. That shows that it has to be an induced interaction where J is the strength of the coupling between a local spin and the background electron. So everything is determined by T star, and it's quite large when you do the experiments carefully. It turns out to be really large compared to a typical Kondo temperature. So you can sort of forget about single ion effects. You think a little more and say, oh, that means the hybridization has to be collective. In other words, instead of a single local moment hybridizing against this background, at least a pair of them must go at the same time. They're typically of opposite spin. So they hybridize together as a result of their interaction. It's a very different kind of instability than the Kondo instability. And this is the reason why it's been extremely hard to develop a microscopic theory of heavy electron materials. The optical measurements show that the so-called hybridization gap, a gap between what you see optically very well, that this depends on T star, not on TK. And the quantum critical point then is not set by a competition between single ion and RKK energy scales. It's found at a much lower value of J, the order of 0.17. And what is the tuning parameter for all of this is the effectiveness of the collective hybridization. So how can we describe that? In the two-fluid model, it takes a very simple form. Let F be the strength of the emerging heavy electron system, which we call a Kondo liquid because its behavior is so different from the Landau Fermi liquid. So you have an emergent Kondo liquid characterized by an order parameter F. If you now look at T equals 0, then F is going to be equal to F naught. So that tells you if you've got a quantum critical point, then F will be equal to 1. F equal 1 is the end of local moment behavior. The strength of the local moment part is proportional to 1 minus F. So F equal 1 marks the end of local moment behavior. And that says that F naught is a good tuning parameter. F naught equal 1 is the quantum critical point. If F naught is less than 1, you can say this is a weakly hybridizing system. If F naught is greater than 1, it's a strongly hybridizing system. What's the difference? How do you tell experimentally? Experimentally, if it's a weakly hybridizing system, you're always going to have local moments around. And they're going to lower their entropy by forming a Néel antiferromagnet. So you see antiferromagnetism. At the same time, conduction electrons are there, and they happily superconduct by exactly the same mechanism we proposed for the group rates, namely an attractive interaction induced by their coupling to the quantum critical spin fluctuations. So this is what the phase diagram looks like. High temperatures, you've got local moments interacting with the nearest neighbor interaction and conduction electrons. And you see that, you see Curie-Weiss behavior in the uniform spin susceptibility. Go down below T star, system begins to hybridize. So the Kondo liquid emerges, and you've still got the spins around, but they're hybridized now, so they have a different strength than they did before. So they form, if you like, a spin liquid that's interacting local moments. At still lower temperatures, on the left-hand side, as long as F0 is less than 1, you're going to get local moment anti-ferromagnetism. And this is what you see. And you've got coexisting with the Kondo liquid. So that becomes superconducting at still lower temperatures. And at the moment, when F0 is such a value, that the Tc for the superconducting Kondo liquid is equal to or greater than the Néel temperature, superconductivity takes over, and you cease seeing any long-range antiferromagnetic orders. All you have is superconductivity. So that's what the phase diagram looks like. But the other really interesting features, there's a line there called TL. What is that? That's the line below which you have only itinerant electrons. Because F0 is greater than 1, it's easy to see, but then you can get F equal 1 at a finite temperature. And that line TL, it marks then the boundary between localized and itinerant behavior. Above it, you're always going to have some local moments. Below it, you only have itinerant behavior. Not shown there is one more fascinating aspect of heavy electrons. That's quantum critical behavior, because you can see that in the transport experiments. And what it does is to cut off the scaling behavior that's seen in the Kondo liquid. It shows a very different temperature dependence, and you can begin to sort out in detail the nature of the quantum critical regime, out of which, in fact, in general, superconductivity arises. What was surprising to us is that if you now take the phenomenological theory seriously, you have a very simple expression for your density of states for the Kondo liquid. And it's going to notice that it's going logarithmically like T star over T. And the relative strength of the local moment is 1 minus F. You have a Néel temperature that's reduced by the 1 minus F times T star, and the strength of the moments is down by a factor of that to the 1/2. Given all of this, you can then predict what might be the Néel temperature of actual systems, and you do very well. And what is surprising with my one-time postdoc, now colleague, Yves, we were able to develop the equivalent for spin fluctuations in the heavy electron materials of the critical transition temperature. It takes the form shown there, and is what replaces the Debye energy is something like 0.14 times T star at the point at which the TL crosses TC, that's TM. And you have a simple expression like that, and that actually explains the variation of TC. that you see in both the rhodium-115 and the cobalt-115. That's the dimensionless coupling strength. Here's a picture of how well we were able to do. So in the top left, you see the dimensionless parameter that I mentioned. The top right shows the way in which these materials are behaving as a function of doping or pressure, and then the predictions of our theory, phenomenological to be sure, for the Néel temperature and the superconducting temperature are shown in the bottom left and the bottom right. And it's pretty amazing that with a tiny set of parameters, most of them obtained from experiment, you can nail the variation in TC that you see experimentally for these materials. Okay, so what have we learned? Well, first of all, there is a strategy that all of the things I told you about have in common other than the plasmons. Namely, we try to use phenomenology as a bridge from experiment to microscopic theory. And I argue this is the only sensible strategy to adopt when you're studying emergent behavior in quantum matter. You start with experiment, you look for regularities, you try to sort out, of these, what might be the most important origin, and then use that to carry out a phenomenological description of what goes on. And if that does a pretty good job of explaining experiment, then you make a toy model that embodies the organizing principle that you arrived at phenomenologically. This is, in fact, if you look back on BCS, that's exactly the way superconductivity developed. One had, first of all, experiment, one had the phenomenological two-fluid model, one had the model that Bardeen developed for the energy gap, which he described in enormous detail in a Handbuch de Physik article written the year before the microscopic theory. He had a quite complete phenomenological explanation of what was going on. All one had to do was to get to the energy gap that he showed would fit all of the experiments. And that was the step which Schrieffer made. So we have a strategy for dealing with emergent behavior in quantum matter first. We learn that particle interactions can give rise to collective modes, but sorting out the effective restoring forces is non-trivial and has yet to be done really microscopically. But the phenomenological approach we developed in Urbana seems to work really well. And was predictive. We predicted the behavior of the modes seen in the helium-3 before they were seen experimentally. We also learned that collective mode-induced interactions can change repulsion to attraction and give rise to both conventional superconductivity and unconventional superconductivity from the quantum critical magnetic fluctuation. And finally, we've learned that condensed matter concepts are absolutely essential if you want to understand neutron stars and understand pulsar behavior. And it's an absolute marvelous playground. I argue the field has, it's developing, there's a lot more that is to be learned. And finally, one can identify collective hybridization in the Kondo lattice materials, and we've set the stage for the development of the microscopic theory. It may take a future Ken Wilson to work it out, but at least one knows how to start, which one didn't know before. So in conclusion, I have a lot of people to thank: my students, my postdocs, my colleagues, my mentors, and I would add to the mentors probably Conyers Herring, who played a major role in my life. For about 5 years, whenever I wrote a paper, I'd send it to Conyers before I sent it off for his reaction before. And it always was interesting and always was fun. And I've really had a wonderful time. And finally, let me say, how is it I'm in pretty good shape at age 92? I attribute it to a number of things. First of all, it's genes. Second, it was having a terrific marriage over 67 years with an enormously supportive wife and enormously supporting kids. Third, it was to be always involved. I never even thought about retiring, nor do I now. Be committed, be involved with something. And this combination of things, plus having a great network of friends, former students, colleagues, and so forth, this is quite enough to, I think, keep you going well past your 10th decade, well into your 11th. And I certainly am determined to try to do that. Thank you. I missed that part.
I heard your last sentence, that you want to decon beta and make it into 8 decades.
Yeah, right. Well, Hans Beta was both a good friend and my total hero. I mean, Hans was just amazing. He did something that I'm not doing. He was calculating well into his 10th decade. And I didn't, we've got a little time, so I'll tell you, how did Hans work? I learned this from Jerry Brown, who was his close collaborator, and at times would take care of Hans when Rose had to go off and take care of his parents. Hans gets up in the morning and runs a very hot bath. Gets into the tub, sits there for about half an hour, 40 minutes, during which he plans the calculations he's going to do that day. Gets out of the tub, drives off, gets Jerry fixing breakfast, and starts calculating. And that I can't match. I stopped calculating the life around that. I just try to stay in there with ideas and trying to write collaborate. That's what I'm doing. So for the moment, what, 25 years in a string and it's just it's safe place and observers look up there and they see what's there and they try to figure out what's what. And they have turned up 2 wonderful mysteries. One of which we sort of understand, the acceleration and cosmological. That's an easy answer to that is, okay, that's 0 point energy and all the stuff is around that. These be responsible for that. Dark matter has something else again. Dark matter is really amazing mysteries. You start off discussing this earlier. You ask the question, what dark matter, single particle sitting around? Probably not, because where's the gravity? Everything has got to feel a gravitational field. So unless dark matter interacts with a long-range force, which is more repulsive than the gravitational force, it's going to crack. And we are presumably looking at cups of dark matter. And then it's really fun to start your scenarios at a cosmological level. So is the dark matter. You have dark matter neutron stars, the equivalent of that. The dark matter, you have stars that have condensed, and so forth and so on. It's a wonderful time to be an observational cosmologist and to be a theorist who follows observation closely. And LIGO, of course, is another wonderful example.
In your opinion, what's the best way to use the version between light and non-light? What is the best way to use emergent behavior concept to tell the difference between light and non-light? Really subtle question.
Well, there's presumably the Turing test, right? But what makes living matter so different? Well, there are a whole set of things. It's fun to sort of trace it out. So you start with Luca, the last universal common ancestor. All of life can be traced back to the molecule that figured out how to self-replicate. But that's only the start of the story. Because along the way, then one developed all these neat ways of having these little motors that generate energy and play an enormous role in our life. And the other thing which makes it fascinating and really hard is all of what we see in living matter is the product of evolution. Evolution had a lot of time to fine-tune. There may have been just a handful of organizing principles, but each of these has been fine-tuned by evolution to make them so elegant. It's really hard to work your way backwards and imagine what was going on in the beginning. And for sure, again, you would say, Luca formed not in a nice equilibrium situation, probably formed underwater, accompanied by volcanoes in a totally non-equilibrium driven situation. Why do I say underwater? Because we are mostly made of water. And the simplest assumption is to say, oh, that must have happened from the beginning, that you had this happy molecule in water replicating away, and the rest is history.
David, thank you. Thank you. We actually have to go.